Hello everyone, welcome to lecture 51 of the NPTEL course on Riemannian geometry. So we basically have 2 weeks remaining in the course. So the theme for the rest of the course, so 2 weeks or 10 lectures, is going to be this correspondence between curvature and topology, or this relationship between curvature and topology. So on the one hand we will see that if the manifold admits a Riemannian metric of a certain curvature property, then that restricts your the topology of your manifold. And then of course one can turn this around and say that if your manifold is of a certain topology, then it cannot admit Riemannian metrics of a certain curvature, right. So it sort of goes both ways. So in order to do this, we'll spend the next this lecture and the next lecture recalling some basic properties that we study, or basic notions that we study in a first course in algebraic topology. Namely, we'll need the notion of a fundamental group and we'll need the notion of covering spaces, right. So in today's lecture I am going to talk a little bit about fundamental groups, and in the next lecture I'll talk about covering spaces and the relationship between fundamental group and covering spaces. Alright, so as I said, the topic for this lecture is to discuss the fundamental group. So of course this can be done over an arbitrary sort of nice enough topological space, but we will restrict attention to only smooth manifolds, since that is the category that we really care about. And then especially these theorems involving covering spaces, you always have to add various adjectives to a topological space, namely that it is locally path connected, locally various other properties, which it turns out a smooth manifold satisfies all those properties anyway, right. So it is easier to state these results for a nice topological space like a smooth manifold. So let M be a smooth manifold. Okay. So let me just remind you, by definition, whenever I say a smooth manifold, M is already connected. Okay. So I think when we reviewed smooth manifolds in the first week, I had said that for us smooth manifolds by default will be connected. Okay. So I will not repeat this assumption again and again. So I fix a point P in M. Okay. So here is a definition. The central the key definition is that of a homotopy of curves. Okay. So let gamma naught gamma 1 be continuous curves. Okay. So then we say that gamma naught is homotopic, right. So we say that gamma naught is homotopic to gamma 1 if there exists a continuous map H from the square 0 cross 1 times 0 cross 1 to M such that H of 0 comma t is gamma naught of t and H of 1 comma t is gamma 1 of t. Okay. So the picture is, let us say you have two curves gamma 1 and gamma naught, then essentially you want to the notion of homotopy allows you to deform gamma naught to gamma 1 continuously. So the picture is the following. So then you have these sort of horizontal slices. These horizontal slices correspond to to curves that deform gamma naught to gamma 1. Okay. All right, and then we call H a homotopy between gamma naught and gamma 1. Okay. All right, so let me maybe just make a quick remark that if gamma naught and gamma 1 are smooth or more generally piecewise smooth, and are homotopic, then one can choose the homotopy H to also be smooth or respectively piecewise smooth. Okay. So, homotopic just means that even if your paths are smooth, you a priori only have a continuous deformation from gamma naught to gamma 1, but then one can actually regularize this and make it into a smooth deformation or a piecewise smooth if your original curves are piecewise smooth. Okay, we need another definition. We say that H is proper if it actually keeps the endpoints fixed. So that means that these are independent of S. Okay, so of course this makes sense only if in particular the original curves had the same endpoints. Okay. Right, so now I want to do the following. I want to restrict attention to loops at a point P, at my base point P. Okay, so we restrict attention to the space of continuous loops at P. So this is basically the set of all curves gamma from 0 1 to m such that gamma of 0 is equal to gamma of 1 is equal to P. Okay. Okay. So then one can look at we have the following definition. Let gamma naught and gamma 1 be two continuous loops at P. We say that gamma naught is equivalent to gamma 1 if there exists a proper homotopy from gamma naught to gamma 1. Okay. So that means you let us say you have your gamma naught in red, and let us say we have gamma 1 in green, then the idea is you can continuously deform gamma naught to gamma 1 through paths that sort of that are basically loops again at P. Okay. So then we say that gamma naught is equivalent to gamma 1, and then the key observation is that this is indeed an equivalence relation. okay, at so this is an equivalence relation on the space of continuous loops at P, okay. So this is an easy thing to check. You have to check that this is symmetric, reflexive, and it satisfies the transitive property. So then we denote the equivalence class of a loop at P by the usual notation by square brackets gamma, okay. Right. So, so the next thing we want to do is we want to define some sort of product on this space of continuous paths, okay. So, so here is a definition. So, let me first make an informal definition and then I will make a formal definition. So, so let us say I am given two paths alpha and beta in this loop space. So, the informal definition is the following. So, we define alpha dot beta to be the concatenation of the two paths of alpha followed by beta, okay. So, that just means that you first traverse along alpha and then you traverse along beta. If alpha and beta are loops at P, then this new sort of concatenation is also going to be a loop at P, okay. So, more formally we define this as follows. So, we define alpha dot beta to be another path 0 1 to m, and the formal definition is as follows. So, alpha dot beta of t is going to be alpha of 2t, where t goes between 0 and half, and it is going to be beta of 2t minus 1 as t goes between this, okay. So, then we also define the inverse path. This is something that we already sort of defined when we talked about parallel transport. We also define the inverse path by this. So, you just traverse alpha in the reverse direction, okay. Now, the thing to note is that right. So, a remark is that this product may not be associative, i.e., so in general this will not be equal to alpha dot beta dot gamma. One can easily just write down the definition on the right and on the left, and you see that they may not be equal. So, in order to define something that is associative, so that you can define a group structure, we have the following proposition. So, that is where this equivalence relation comes in. So, we have the following fundamental proposition. So, firstly, if alpha I and beta I are loops for I equal to 1 or 2, such that alpha 1 is equivalent to alpha 2 and beta 1 is equivalent to beta 2, then their products are also equivalent, okay. So, this is not too difficult to check. Similarly, if you take alpha dot alpha inverse, that is actually equivalent to the identity path. So, here this is the constant loop identity of t is equal to p for all t. Okay. And the third point is that even though you do not have associativity, you do have associativity up to this equivalence relation. Okay. So, the upshot is that if you define this set pi 1 which by definition is simply the set of loops modulo this equivalence relation. So, it is a set of equivalence classes of loops at P, then this dot induces a product and hence a group structure on okay. So, this group is called the fundamental group. So, let me make that definition. So, pi 1 of m with the induced product sorry I should be careful, I should have a base point here. So, pi 1 of m comma p, because you are looking at only loops at P. So, I should have a base point. Is called the fundamental group of M based at P. Okay. Right. So, now a natural question would be what happens if you change the base point. So, for that we have the following basic proposition. So, for any P and Q in M, if you look at the fundamental group based at P, that is going to be isomorphic to the fundamental group based at Q. Okay. So, at least up to isomorphism your base point does not really matter. So, hence one can talk about the fundamental group of a manifold or a topological space, of a connected topological space. Okay, so what is pi 1 of M? You basically choose a base point and look at the fundamental group based at that point. Okay, now if you choose a different base point, you are just going to get an isomorphic group. So that is why you can talk about the fundamental group of M. Okay, so let me quickly indicate how to prove this. The idea is very simple. So, you have your point P and you have your point Q. The key thing is that M is connected, which as I explained is by default all our manifolds are connected. So, given any P and Q, they can be joined by a curve gamma. Okay. All right. So now suppose you have a loop at P. How do you get a loop at Q? The idea is that you basically transport this loop over to Q by going via gamma. So in other words, you first go by gamma inverse. So so you have the following map from here to here. So you take the equivalence class of some loop, then this is precisely going to be, you first go by gamma inverse back to P, then traverse alpha and then go back by gamma to Q. So the point is that this is actually well defined. What does that mean? That means that if you choose another representative instead of alpha and do this, then you are still going to get something that is homotopic to gamma inverse alpha gamma, right. So firstly this is well defined and one can check that this is an isomorphism, okay. So this involves a little check, it is not very difficult. So if you have not seen this in a course in algebraic topology, you should try to just do it by yourself, okay. Alright, so I have one final definition before I give you a few examples. So we say that M is simply connected if the fundamental group of M is trivial, okay. So informally what this means, every continuous loop can be continuously deformed to a point, okay. Alright, so maybe let me make another remark and then we'll move on to examples. So note that pi 1 of M need not always be abelian. So this product that is induced on pi 1 of n need not actually be a commutative product, right, and in fact we will see an example at the end of one such manifold M for which this is not abelian. Okay, so let's look at a few basic examples. So the first simple thing is that if you take the Euclidean space, then the fundamental group of that is trivial, okay. In fact if you take any sort of convex domain, you can always show that a convex domain in Rn, you can show that its fundamental group is trivial, because you can always homotope along straight lines, okay. The first sort of non-trivial example of a fundamental group that we learn about in a course in algebraic topology is that of a circle. So if you take the fundamental group of a circle, that's the set of all integers, and these integers essentially correspond to how many times you can wind around the circle, right. So this integer z counts the number of times your loop is winding around the circle. So there are actually two proofs of this. One is via complex analysis, okay, using this notion of winding numbers. The other proof is via covering space theory, okay, which I mean we'll cover, we'll talk about covering spaces in the next lecture, but of course we will not be proving this, but as an application of what we talk about, one can prove that the fundamental group of S1 is the set of integers. So a reference of course is the standard book of Hatcher, algebraic topology. Okay. So you can refer to that. I mean in this and the next lecture I am only going to be making statements. I am not going to be giving you many proofs because all the proofs are quite standard if you have taken a course in algebraic topology. If not, then I think it will take us too far away from our main goal if we start proving all these results. So I would suggest that if you have not taken a course in algebraic topology, I would suggest that you look up these statements in Hatcher's book, and that would be a good way for you to also pick up a little bit of algebraic topology on the side, right. Okay, so so that is essentially the first non-trivial fundamental group that we learn about. Then using this one can show that pi 1 of C star is also Z. So here C star is just C minus the origin, okay, and the reason is simple that that C star can be actually deformed, or in topology you say that it retracts onto S1, okay. So one can deform C star to S1, and then a basic property of fundamental groups is that that it is invariant under deformation retracts, right. So so because we know that the fundamental group of S1 is Z, fundamental group of C star is also Z. So this should sort of tell you that the informally, and that is actually a good intuitive way to think about it, informally pi 1 measures the number of holes in M, right. Okay, the fourth example is that of a sphere. So one can show that that of course if n is 1 then this is a circle, then we have seen that this is Z, but if n is strictly bigger than 1 then the fundamental group turns out to be trivial. So a higher dimensional sphere for n bigger than 1 is always simply connected. So for S2 for instance you can sort of see this intuitively that if you have any such sort of curve that any such closed curve, you can sort of see that you can always deform this to the north pole, right, continuously without tearing the curve. So intuitively it seems reasonable that the fundamental group of S2 and then of course S3, S4 etc. they are all trivial. Right, my last sort of class of examples is again an important class. So you let sigma g be the torus with G holes, okay. So so we saw when in our discussion of the Gauss-Bonnet theorem that all oriented two dimensional smooth manifolds are basically given by a sphere with G handles, or that is just a torus with G holes, right. So the picture is that for G equal to 0 you have your sphere, then you have your regular donut, the usual donut for G equals 1, and then a donut with possibly multiple holes, okay. So then it turns out that of course we have seen that pi 1 of sigma naught is trivial. Sigma 1 is basically diffeomorphic to a product of two circles, and so then one can show that that pi 1 of sigma 1 is simply z cross z, but more generally pi 1 of sigma g is basically just a free group generated by 2g elements, okay, such that the product of the commutators of these guys is 1. So, commutator is just A B, A inverse, B inverse. So, if you multiply all these commutators together, then that is 1. So, it is basically a free group generated by these 2g elements with a single relation which is given by this product of commutators being 1. And so, for g bigger than 1, this is non-abelian. Okay. Alright, so these are some of the sort of examples of fundamental group. So, I should note that here your fundamental group is generated by these two circles, and then you have the same thing for a higher dimensional torus, except now there will be some relation amongst so these generators are not completely independent. Okay. Alright, so maybe that is it for this lecture. In the next lecture I will talk a bit more about covering spaces, and then we will again go back to geometry and try to prove theorems of the kind that if the curvature satisfies a certain condition, then the topology is restricted. Okay. Alright, so thank you for your attention, and that is it for now, and I will see you in the next lecture. Thanks.